Good afternoon, everybody. So far we handled all types of materials that can be used as a biomaterial, and we went through the different classes of materials like metals, ceramics, and polymers. And we learned that polymers have these very specific features because they can be specifically functionalized, and you can do a lot of different things with polymers that you not can do with metals and ceramics. And one of the intriguing features of polymers is that we can adjust the hydrophilicity or hydrophobicity. In other words, we can adjust the properties, how polymers interact with solvent, especially with water. And this makes polymers interesting because if we now get entangled structures of polymers, what we could do is we could make something that is called a hydrogel. What is a hydrogel? Well, a hydrogel is a polymer network that can significantly take up water, and this will lead also to swelling. So you can have either one polymer, then this is a mono or homopolymeric network, or you can have several polymers, then you talk about copolymeric networks or interpenetrating networks. So what does this mean? Well, this means that you have a tiny little amount of material, which is the polymer, and in a hydrogel this can be around about 2 to 3 weight%, and the rest, 97 to 98% of this material is water. And this makes it very useful for a lot of biomaterials applications because now in this interspace between the polymer chains, you can now integrate living materials. You can integrate cells, you can integrate biologicals, you can integrate other proteins, drugs, and so on. So the question is, how can you keep these polymer strands now in place? So when you have like this mesh, this network of these polymer strands, and now the water gets in, and we will have a look at that in a minute, how can you actually place these polymers so that the water just not disrupts the entire structure? So the interconnection can occur either physically, you see here some kind of entanglements. It can occur chemically, so some knot points where you get some chemical interaction, and you can have some physical-chemical interactions like hydrogen bonds that actually make such a network strong. If we talk about these physical interactions, they are, of course, very interesting ones because they render this hydrogels dynamic. In case of a chemical coupled polymer, you have an anchor point, yeah, and these anchor point now will actually cross-link two polymer strands. Yeah? So this would be polymer 1, polymer 2, and in between we have the cross-link. So if you take this into consideration, it's quite clear the cross-link is quite stiff. So you can use chemical cross-linking for this intention to stiffen a hydrogel. So if a hydrogel is too soft, you can introduce chemical crosslinks to make it stiffer. On the other hand, especially if you think about now replacing tissue, stiff hydrogels are probably not the best choice. On the other hand, you have to prevent the hydrogel from disintegration, and therefore we need physical cross-linking. Physical cross-linking has the advantage that we have much better dynamics, yeah, so that we still have much more flexibility in the hydrogel. But at the same time, we allow the hydrogel to get a bit better connected. And for instance, if we have something like this. And now we consider to have, let's say, a second polymer here. Then in this case, the blue line, the blue polymer will go behind and then makes a loop and comes up front. And now we have this physical entanglement, which means that these blue and the white strands, they're physically interacting, but we still have some dynamics in there, right? So you can pull them apart, you will stretch them. This will have an impact on the pore sizes. And this is, of course, a different entanglement that we get in the chemical crosslink. And the same is true if we think about like hydrogen bonds. So if we have two different polymers that then interact here with hydrogen bonding, what can happen is that you disrupt the hydrogen bonds, the polymers glide along each other, and then they reconnect again with hydrogen bonds at a different spot. Yeah? So this will actually lead to some displacement. And this is also beneficial in terms of biomaterials use, because now consider a cell sitting inside such a network, pushing, pulling, ripping this up like a zipper, and then relocating or coupling these polymers in a new place, where the cell now actually has expanded the room in which it can move, but still the entire network is stable. And finally, a third possibility of physical interaction is metal chylation. So you can have two strands, and they do have side chains that are now actually able to chelate, for instance, metal ions. And this is also a very nice feature of physical physical linking, because now by adding or removing the metal ions, you can open or close the interaction. So if you think about drug delivery, yeah, you can actually load the gel in an open position, add the metal, it closes, and as soon as you remove the metal, it opens again, and then the drug releases. So physical crosslinking has a lot of benefits, especially if we talk about biomaterials applications. But in some cases, we need, for stability issues, also chemical crosslinking. Yeah? Because as long as we do not have these entanglements, if we just have these kind of interactions, they are very weak and they can be disrupted very easily inside, for instance, a human body. And then you have to additionally add chemical crosslinks. All right. So just to show you exemplarily what happens with a hydrogel, so if you just have the polymer network and it's dried, then it's actually shrinks. So it's a tiny little piece of polymer. And if you place that now in a bowl of water, so the red dots here are intentionally the water molecules, but they can also be drug molecules inside the water. The water diffuses in between the polymer chains, and if they physically actually just expand the polymer chains. So we have a stretching until the points of crosslinks are reached, either the chemical points of crosslinking or the physical points of crosslinking. And this swelling behavior is sort of a thermodynamically driven equilibrium reaction, right? So the interaction between the water and the polymer induces the swelling. So this is some osmotic force that actually is applied to the polymer, and the stretching of the chains lowers the freedom of conformational flexibility. So you lose entropy. And the entropy loss induces then a restoring force. And this now again has some implications on the polymer you choose for the hydrogel, because this restoring force will depend on the molecular weight and the degree of stretching. So you can take one and the same polymer and just vary the molecular weight, and you can actually induce a completely different restoring force. That means you can make a hydrogel out of a polymer at a low molecular weight, and this will behave differently. It will be much softer than the same material in a hydrogel with a higher molecular weight. Yeah? So besides tuning chemical crosslinks and the physical crosslinks, you can also tune the molecular weight of a polymer. And this will also have an impact just based on thermodynamics on the behavior of this hydrogel in contact with water. And now, of course, you have to consider that the swelling has an influence on the applicability. So because swelling will allow metabolites to diffuse in, but also to diffuse out. Again, think about drug delivery. So you could actually load a drug into a hydrogel, and then you just dry it. So the drug is encapsulated. Yeah, it's a dry capsula. Now, if you inject that into a liquid environment, if you just orally take that up and it becomes liquid again, the hydrogel will swell and the drug will be released. Actually, companies do that a lot, for instance, in the food and the nutrition applications. So you can have flavors encapsulated in a dried hydrogel, and as soon as you eat them, the flavors are set free, and then you get all these nice flavors you like. Yeah? But in order to protect them and to store them, they're encapsulated and they're dried in a hydrogel. So that's a very simple trick that food industry uses, for instance, to protect flavors and set them free right at the point where you eat them. Of course, the swelling will have an impact on surface properties. So remember, we talked about applications of biopolymers and polymers as biomaterials. And we had the examples of, let's say, contact lenses. So if the surface properties change upon swelling, you might have an impact then on the surrounding tissue, like on the eye, right? So if the surface gets rougher, you might have some shear forces that apply. You get inflammation, you get the eyes will hurt or they will run dry, whatsoever. So you have to be aware of that the surface properties of a hydrogel will change upon swelling. And finally, the same is true for mechanical and optical properties. If we again go back to our contact lenses, it might very well be that upon swelling, you get some opaqueness. Yeah? So light doesn't go through anymore. And this, of course, is a downplay for having contact lenses. So because you want to have these optical clearance and you do not want to change the optical properties upon swelling when you put the dry lens into the liquid eye, right? And I think it's also clear that mechanical properties will change because in the dried state, we have a much higher stiffness of the materials in comparison to the swollen, much softer state. All right, so if we consider polymers and hydrogels inside a human body, we not only have to take care of the mechanical properties, the optical properties, and the surface properties, we also have to take care of the durability. So how long can the polymers withstand the human or the body environment? So when we talk about metals, when we talk about ceramics, there is a very slow degradation process. We have corrosion in terms of metals. In terms of ceramics, the body is really not degrading the stuff. With polymers, that's quite different. So therefore, in the next section, we will focus on degradability of polymers. So what do you think? How do polymers behave in a human body? So if you inject polymers, microplastics is a big issue. Yeah? So we take up plastic with food. What happens with this plastic inside the body? What do you think? Can you digest this? Does it circulate in your body? What happens to plastics that you take up?
It size of the microplastics is really small, then cells can take up and it can interfere with the cell metabolism.
Okay, so I repeat the answer. So it depends on the size of the microplastic particles. If they're small enough, they can be uptaken by cells. That's right. And what happens then in the cells? Will they be degraded, or will the cells uptake as many particles as they can? But what happens then when they're filled up?
Accumulation of those microplastics in the body.
Okay, so there will be accumulation of microplastics in the body. But then again, I mean, all of you very likely already consumed microplastics. If we would cut you open now, which we of course are not doing, will we find plastics really somewhere, or is there somewhere a deposit in the body, or what happens?
It can be degraded by some enzymes.
Yeah, so degradation is of course a big issue, right? So enzymes, environmental conditions, they play a role. So let's have now a look at the biodegradation of polymers. So in principle, we decide between biodegradable polymers and non-degradable polymers. But I would like to draw your attention already to the last line. If we consider a polymer in the context of a human body, all polymers, no matter what, will be attacked, will be degraded to some extent. It's just a matter of time. Yeah? So let's start with the biodegradable polymers. So biodegradable polymers, they obviously can be degraded quite rapidly because they contain functional groups that can be degraded. And these functional groups that allow then the opening of chemical bonds. And if you have these degradable polymers, they are very useful in terms of drug delivery or as drug depots, but also in tissue engineering, especially in biofabrication. So when you first provide a scaffold in which new tissue can grow, you actually would like to have the scaffold replaced. Yeah? As soon as the tissue is growing, you would like to remove the scaffold. And you do not want to do that by surgery. Best way is to do this by biodegradation. So it makes a lot of sense to have polymers that degrade with a certain rate, so within a certain time, not too early, not too late, to allow tissue regeneration. How about the non-degradable polymers? The point is, they are also degradable, but it's just very slow. Yeah? And again, if we go to the argument with microplastics, I mean, we do have plastics that are degraded, but it takes hundreds and thousands of years if they are just in the environment. We have to consider a human being is not living for 1,000 years. So obviously, inside the body, the environmental conditions are much harsher than in some environments out there. And this is coming to a surprise for many people, yeah? That inside our body, we have much harsher conditions than like in an ocean. Yeah? Because we have this combination of enzymes, you mentioned it, of different ions, of cells, and they all play a role in this big picture. So when we actually use polymers for implants, they, of course, these non-degradable polymers, they can maintain a function over a longer period. And if you remember, we talked about this total hip endoprothesis, where we have this hip socket, which is made of highly molecular weight polyethanol. This is a non-degradable polymer, as we would say. But still, after 15 or 20 years inside the body, we will see some degradation on the surface. And therefore, these implants have to be replaced over time. All right. So, what are biodegradable bonds? So, what is the major issue if we talk about polymers inside our human body? What do you think? What is the major driving force for biodegradation? What is the major driving force? Yeah.
Everything, some component of the blood.
Blood components. So we have, I would say, catalysts. Yeah, if we claim that chemically we have catalysts such as enzymes, but also we have salts, we have acids, we have bases. But what else? What's the major component of our body by weight? Yeah. Water, exactly. So water does play a critical role. Why? Because water can attack chemical bonds, and then you call this hydrolysis. And the very interesting point is that especially our biopolymers, they are made by a chemical reaction that is called a condensation reaction. What is a condensation reaction? Well, it's the formation of a new chemical bond upon removal of water. And since any reaction is always an equilibrium reaction, you can actually go the other way around. If you add now water, you can split this bond again. To make this quite clear, just draw here a very simple molecule, and if we now add some water here, and we can add an enzyme, and we can have some acidic or basic conditions. What you then make out of this compound is actually a carboxyl group, so you make an acid out of that, and you generate an alcohol. So this is what we call hydrolysis. So these are the catalysts, but actually water can do this on its own. It just takes too long, right? So it's a slow process hydrolyzing such a chemical bond, but it could taken also on its own. To speed this up, we need enzymes. And that's exactly the point. So therefore, inside a human body, almost any polymer will at some point be attacked. The question is just, are these sensitive bonds that can be hydrolyzed accessible? Yeah? So that's the big point. We have some influencing factors. And this, of course, will be the chemical structure. So, for instance, what would be R? That's one point. Then, of course, the morphology. Will this be covered? Is it somewhere inside the structure? Is it on the surface? And again, and we had this already with the hydrogels, it can depend on the molecular weight. So that's the reason why in our hip implants we have these ultra high molecular weight polyethylene, because this is very slowly degradable. If we just would take classical polyethylene, this will be degraded much faster. Yeah, that's the impact of the molecular weight. Chemically, there is no difference. Just the molecular weight, because this has impact on morphology, on the accessibility of the chemical structures, and this is something we have to consider if we talk about the degradation of polymers. Okay. So, what is hydrolysis? Just in a chemical sense? Well, it's a first order reaction, and a first order reaction means it's quantitatively proportional to its initiation. Yeah? So as many starting points you have, or if you have more starting points, you have more hydrolysis, very simply said. So therefore you can accelerate hydrolysis if you increase the number of hydrolyzable groups. Yeah? So if you want to have a very good hydrolyzable polymer, you should increase the number of hydrolyzable groups. Then you have a faster degradation. The polarity of the polymer, of course, plays a role. If you have hydrophilicity, if they have a good water contact, then this is a preferred attack point for hydrolysis, in contrast to having a hydrophobic setting. If you have low crystallinity, now we talk about morphology, yeah? If you have access to the groups that can be hydrolyzed, this makes a lot of sense. Low crosslinking, we talk about the chemical crosslinking now. A high surface to volume ratio, or if you have mechanical stress. Yeah? So if you take a polymer and you put it under mechanical stress, it will hydrolyze much faster than if it's not stressed. So again, it depends on where inside your body you make use of the polymer. In reverse, hydrolysis will be slowed down if you lower the number of hydrolyzable groups, if you increase the hydrophobicity, if you have a high crystallinity, a lot of cross-linking, low surface to volume ratio, and you have low mechanical stress. So I think that makes a lot of sense. Now we will quickly go through different polymers, and they're just now grouped into degradable, non-degradable, hydrophilic, hydrophobic, and we will see what happens if they come in contact with water. So we start with a very simple and I think straightforward polymer. This is a polyester. It's a polymer with water absorption. So this is what I've already drawn down here. Yeah. This is the polyester group, and when we actually make a hydrolysis here, we get the carbonic acid and the alcohol, which means this polymer will be degraded after we implant this in the human body. And the fact also is with the polyester, the degradation or the hydrolysis will not be just limited to the material surface, so we'll go step by step. Once the first layer is gone, the next layer will be hydrolyzed, and it goes deeper and deeper and deeper because this has always a good polarity and a good water interaction. So what happens if we take a very similar structure? Yeah? So that's the polyester, and we take now a very similar structure like in the polyurethane, but now without water absorption. So polyurethane now is more hydrophobic. Well, we also will have hydrolysis here, and we will have now three products. We will have an amine, we have an alcohol, and we will have carbon dioxide. So these are the three products. Such polymers won't be hydrolyzed to begin with, but slowly after implantation. So, for instance, polyurethanes can be used as replacement materials in the Achilles tendon. So you have to be aware of that the hydrolysis won't go on within the first 5, 6, 7 years, but then over time this can happen and you can actually get these kind of byproducts. But because the polyurethane is not uptaking water, the degradation will be limited to the material surface. Yeah? So therefore you do not have to replace, if you have this as an Achilles tendon replacement, or at least repair piece, you do not have to replace this because it will not be fully hydrolyzed since hydrolysis is only on the material surface. So it will lose some properties of the original implant, but it will not completely fail. Yeah, that's important to know. So now let's go to non-hydrolyzable polymers. How will they behave inside the body? So there is no group that can be hydrolyzed, like a vinylic polymer here, like the polydimethyl acrylate, or inorganic polymers like polydimethyl siloxane. no hydrolyzable group. Water cannot attack these groups. Still, we see slow degradation. What happens here is these molecules, they still have affinity for water. And this is pretty much similar to what we've discussed with the hydrogels. Just the water uptaking abilities are much smaller. But what happens is that water can interpenetrate in between the polymer strands, and this will lead to structural changes, slowly. But it will, and actually the water again will have the osmotic pressure, and this will then break bonds. Yeah? Even hydrophobic polymers can absorb small amounts of water, and then we have these osmotic forces that will disrupt chemical bonds, and this actually starts then to degrade the polymer. Now, that is sort of the most durable material in terms of implants, and it's also used halogenated hydrocarbons like Teflon. So for what do you think Teflon is used inside our body? Any idea? It is used as implant material. For what? Yeah.
Maybe for some knee joints?
I don't know.
For stents?
Stents, so anything where you have contact with bloodstream. So bypasses or vascular structures, because blood is the most extreme and most aggressive liquid we have inside our body. And therefore you need something like Teflon that does not absorb water and that's not hydrolyzable. So halogenated hydrocarbons, they have within a human's life cycle no degradation. Yeah? And there's no or little structural changes because they really cannot uptake water. So that's the only polymer class that really can withstand a human's lifetime without obviously being degraded. There might be other drawbacks with Teflon inside the human body, but at least this is one polymer that has no visible and no obvious degradation once it's implanted. So, if we now want to engineer a polymer for an implant, let's consider design criteria. Yeah? So what will be the design criteria? Well, the design criteria will be very likely driven by the application. Yeah, because it will depend on whether we want to have them quickly degraded, slowly degraded, not degraded at all. So that's one point. But then we also have to think about the morphology. So the design criteria not only come through the chemical features, but also through the morphological features. So we have here chemical features. We have morphological features. And now we actually, when we are good at this, we finally get a design. So if we have now these finally designed polymers, of course we have now to double check whether they fulfill all the criteria that we listed. What would you do to actually now check if the polymer is suited for the application for which we actually designed it? what would you do? Considering the degradation points that we had here before.
Yeah, you have to test it. It's like if we expect them to be in the bloodstream for a couple of months, we have to test it for a couple of months before.
Okay, that's good. So the answer is, of course, testing. That's right. So you mentioned now something really important. If you want to use this in the bloodstream for several months, you said you have to test this for several months. Now I give you a drawback. The problem that actually has been found in the past is that degradation in vivo, so in the human body, is much faster as in a simulated lab situation. That is a very, very crucial point. And the second point is that it will be individually different. So if you put a polymer in your body, it will probably degrade differently than in your body, and then in your body, and then in your body. Why? We have enzymes, we have salts, we have a cocktail of different things. And we also have something that I have forgot to add here. We also have free radicals. Free radicals play an important role in the defense of our body against foreign materials, especially bacteria, viruses, fungi. So everything that intrudes our body and doesn't belong there is attacked. And it's not just attacked by cells, it's also attacked chemically, yeah, by setting free radicals. And we even have enzymes that make these kind of free radicals. So therefore, this has to be taken into consideration because typically we don't have free radicals in the laboratory when we test for degradation. And now coming back to the different settings, and of course this cocktail of enzymes, salts, free radicals is different in anybody. So we can very hardly predict how the polymer is behaving in your body. We can't just do this like on average. Yeah? And this is also one of the reasons why implants go well maybe for 98% of the patients, but 1-2% of the patients have problems with the implant. Yeah, because they do have a different response to the material. Getting back to a material scientist, having this in mind, that the degradation in vivo is much faster because we have highly complex cocktails of different additives, we have to simulate that here. And how this is done typically, if you make degradation tests in vitro, so in the laboratory, you actually add a lot more enzymes that will typically occur inside your body. So proteases and stuff. So you overdo, so to say. You want to speed up things and see what happens under worst case. Yeah? This is how you typically deal with these issues. So you add a lot of stuff, much more than the implant, the polymer will see inside your body, and then you actually monitor the reaction, and then you get a first feeling. But still, this doesn't tell for sure how the polymer will behave inside your body. So when we talk about polymers and implants, we talk now a lot about synthetic polymers. I think it's also clear that, well, we could use polymers that are already made in nature, so-called biopolymers, like proteins, polysaccharides, polynucleotides, and use them as a material. Why not? Yeah? Advantages would be, since they're already used in nature, they're probably less toxic than something that is petroleum-based. It's probably causing less inflammation, and they should all be biodegradable, because this is the stuff our bodies are used to deal with it anyhow. However, there could be some disadvantages, because once this biopolymers come from a different organism, it could trigger immune response, right? Because it could be a signature of, oops, there is something weird ongoing. We have an intruder. There's a bacteria coming. That could be counterproductive. The next thing is that the polymers that we discussed so far, the synthetic ones, they're very simple, right? So there's tiny little monomers, and then they're just polymerized. If we think about a protein, very complex, we have 20 different monomers, amino acids, which are then polymerized. So we have a much higher complexity in the structure, in the morphology, and most of the biopolymers do not even have the mechanical strength to replace something like a bone. And now I would like to introduce something to you that we're currently working on, or we work since 20 years on that, material in nature that is world famous for its mechanical properties. And that is spider silk. And I brought you exactly this badminton racket today so that you can have also then a glance at it. So it's very simple. You just take a few spider webs and then you just turn the racket. And this is pretty much how you make this racket. And you can see I can already, put my hands in there and you can play with it. You can play ball. Now, why is this so intriguing? Well, it's intriguing because you have to consider that the individual fibers here, they are 5 micrometers thin. 5 micrometers thin. If you try to do this with steel, it's like that. It took us quite some time to find a company to make thin steel fibers. I do not want to touch this because it will break. That's the intriguing point. So the thinnest steel fibers we can make, to have a direct comparison, are 17 micrometers. So they're round about 3 times thicker. Still, you can now compare the mechanical properties of both, and what you will see is the strength of the spider silk is much higher, and this is due to the fact that it combines a high strength and some elasticity. So you see the bouncing ball. Yeah? Now if you try to do the same thing here with the steel, it's even hard to keep it on the racket because it's just bouncing off. Steel is not flexible, it's not elastic, it has no elasticity. And this also means it cannot distribute, see, and it's already broken, and it cannot distribute energy along the fibers. And that's the trick here. So the ball stays centered, and this makes a lot of sense. Just imagine this is a fly, and it flies into the web. It should not be bouncing back, and it should not bounce anywhere else. It should stay where it is, right? And then there's a second trick of a spider. It puts glue on the web so that it's, the prey is sticking to it. So if you like, you can pass this around. I do not pass around the steel one because this is really very fragile, and we did a lot of experiments, and it really is a very lousy experiment. Okay. Now comes the important fact for using spider silk as a biomaterial, because spider silk does not cause inflammation, and it does not cause allergic responses. So it's been known since centuries that you can use spider silk as a wound coverage device. And to show you what you can do with spider silk, I brought you a movie which you can also download from the internet. And this actually explains a bit about spider silk, the properties, and also how we make spider silk without the use of spiders.
Nylon. It changed the world. It was the first ever fully synthetic fiber to be mass-produced and marketed. Elastic, tear-resistant, and long-lasting. a real revolution for the textile industry. But nature has produced an even better fibre, one with properties that have been perfected over 300 million years of evolution. A fibre that can now outshine all the others. Spider silk. That's why biochemist Prof Scheibel is not afraid of spiders. He admires them. His idea was to manufacture spider silk the way nature does, and to take advantage of its properties. The exciting thing about spider silk as a material is that on one hand it's mechanically the most durable material we know. Spider silk combines strength and elasticity. And on the other hand, spider silk is practically sterile. That means it can be used directly on or inside the body. And it's been known for thousands of years. There are descriptions from antiquity about spider silk being used to dress wounds. But raising spiders in large quantities and harvesting their silk naturally doesn't really work, because spiders are cannibals. They would devour each other. That's why, since the 1980s, researchers have been working on a different approach. They want to recreate this miraculous spider silk in the laboratory, using genetic engineering and biotechnology. The basic idea was simple. From the genetic material of the spider, copy the piece of DNA responsible for spider silk. Then insert it into the genome of some bacteria. The bacteria produce the spider silk protein. And then it can be harvested. As simple as the idea sounds, it still hadn't worked after 20 long years. Many researchers had tried and failed to fabricate spider silk proteins in this way. For us, the exciting thing about the process was, why hasn't anybody done it so far? What's so special about these spider silk proteins that it can't be done? And our motto was, nothing's impossible. We were totally convinced that somehow it could be done. One day, the decisive idea came to Scheibel as he was toying with the problem yet again. The gene for spider silk consists of many individual DNA blocks. The researchers usually associate those with short additional DNA pieces. This creates a genetic copy that's not quite exact. So every attempt fails. Scheibel's suspicion was that the connectors were to blame. So what would happen if they were left out? What if Scheibel could find a way to seamlessly connect the DNA sequences for the spider silk protein? And that was also our first patent, this so-called seamless cloning, to produce genetic information without any extraneous sequence, as it's called. And amazingly, it worked right away. But back then, the molecular tools for implementing the idea didn't exist. Prof Scheibel's team first had to invent the method for seamless cloning by themselves. The researchers then used the seamless DNA sequence in intestinal bacteria, hoping that they would go on to produce the spider silk protein. And, lo and behold, after more than 20 years of unsuccessful trials, Prof Scheibel was suddenly the first to recreate this coveted spider silk protein in a laboratory. But only a tiny bit of it. To produce large quantities, they needed lots of bacteria. In a bioreactor, the researchers managed to provide those bacteria with exactly what they needed to mass-produce the spider silk protein. At the end of the process, they had a solution that was full of this sought-after raw material. That first step, using biotechnology to mass-produce spider silk proteins for the first time, was sensational. We still didn't have any fibre, though. That came much later. And the journalists kept saying, if you don't have any fibre, the whole thing is pretty boring. At first, it was a mystery how the researchers would make fibres from the spider silk proteins. It took the team 10 years to decipher the chemical and mechanical tricks inside the spider's body. Then they tried out the natural process in the lab. Finally, they succeeded. From the proteins, they created the first ever artificial fiber made of natural spider silk, meter by meter. Since the genes for the spider silk had been slightly modified, the fibers from the lab were even more elastic and stable. If you wanted to stop a Boeing 747 while it was landing without using its engines or brakes, one thumb's width of spider silk rope would be enough to do it. You'd need a bit of a run out though, around 3.8 kilometers, because spider silk is elastic, but then the plane would come to a standstill. Biosteel is the name Thomas Scheibel has given to his spider silk fiber. Meanwhile, the startup AmSilk in Munich is producing larger quantities of it. For demonstration purposes, a sports shoe has already been made. But sports and outdoor clothing are not the only conceivable applications by far. Thanks to their special properties, spider silk proteins can be used in all kinds of areas. You can also produce other materials with the spider silk proteins, of course. Coatings for implants, like silicone implants, for example. You can use them to package active ingredients, then deposit them inside the body and release them slowly. And don't forget cosmetics too. Now everyone can have silky smooth skin. Of course, we have more products, already available as prototypes, and we're expecting those to arrive on the market in the next few months or in 1 to 2 years' time. So the technological platform to manufacture spider silk proteins is only the beginning. The potential applications seem infinite. The market for textiles and industrial yarns and threads alone is worth around 50 billion euros. There are 45,000 known species of spider in existence, and all the properties of all the fibers they produce have yet to be discovered.
Yeah, so as you can see, we have now a whole new class of polymers, and the point just is we have to actually take the genetic material, we can manipulate that, we produce this in bacteria, we purify the proteins, and then we process this, and this gives us now possibilities to do things that cannot even be done with synthetic polymers. And with this, I come to the end of this lecture. Bye-bye and see you next time.